welcome to Module 2 of this 3-part video series on computer networking for data specialists. My name is Paul Mallet. I'm a data specialist from the Skate Ontario section. In this module, we'll be talking about the computer network hardware needed to set up a competition scoring system. So more specifically, we'll be talking about modems, switches, routers, Ethernet cables, and network adapters. Then we'll discuss using this hardware to configure a network used by CSS. And I will review two scenarios. One is a network used for live scoring using CPC, and that'll include networking a couple of data specialist computers with a DIO, a referee, and some judge computers. The second scenario will be a smaller network used to connect 2 or 3 DS laptops with a network printer that could be used for manual entry of results. Finally, I'll turn my attention to networking video replay systems. Let's start by comparing modems, switches, and routers. Knowing the difference between these devices can be challenging because they might look similar. That is, they might all look like boxes with Ethernet ports. To add to the confusion, in most homes, these devices are not standalone objects, but instead are often combined in different ways. For example, you might have a standalone modem that serves as an interface to the internet via a coax cable or telephone line in the case of a DSL modem, or perhaps even a fiber optic line. Connected to this modem, you might have another device, which is a router and a 4-port switch combined into a single device. And in most such home devices, they may also include a wireless interface to provide Wi-Fi access. Increasingly these days, your Internet Service Provider, or ISP, might only require a single device that includes an integrated modem, wireless router, and switch. But regardless of how your modem, router, or switch may or may not be combined, we can still understand the purpose of these individual functional units. So let's compare them. We've already talked about the function of a modem, which is to connect to the internet. A network switch connects devices within a network, often a local area network or LAN, and forwards data packets to and from those devices. Unlike a router, a switch only sends data to the single device it's intended for, which may be another switch, a router, or a user's computer, not to networks of multiple devices. Routers, on the other hand, select paths for data packets to cross networks and reach their destinations. Routers do this by connecting with different networks and forwarding data from network to network, including LANs or wide area networks, or WANs. In practice, what this means is that routers are necessary for an internet connection, while switches are only used for interconnecting devices. Homes and small offices need routers for internet access, but most do not need a network switch unless they require a large number of Ethernet ports. However, large offices, networks, data centers with dozens or hundreds of computers usually do require switches. And because a typical competition scoring system includes many devices that must be connected via Ethernet cables, they too require both a router and a switch. In simpler terms, a switch is used to connect network devices together. If you run out of ports for the number of devices you have, you add a switch. And if all the ports on that switch fill up, you can add another switch. There are two main categories of switches. Unmanaged switches have no configuration, interface, or options. They are simply plug and play, are less expensive, and they're often used in small office and home office environments. Managed switches have one or more methods, typically a web interface, that allows you to configure the operation of the switch. These are typically more expensive, more complex, and are used in larger business and enterprise systems. Switches can have a varying number of ports and network speeds. On the left is an example of an inexpensive entry-level consumer-grade unmanaged switch. On the right is another inexpensive unmanaged switch, but this one has 16 ports. Both of these switches support gigabit speeds, which means that they're capable of handling speeds up to a gigabit or 1,000 megabits per second. This is plenty for a typical home and certainly sufficient for a competition scoring system. There are faster, more expensive switches and slower, less expensive switches. But these days, gigabit switches have become the standard for home networks. Coming back to the router now. A router brings a lot of the smart functions into a network. It works as a dispatcher, directing traffic and choosing the most efficient route for information in the form of data packets to travel across a network. A router can also connect networks together by routing data packets from one to the other. A router can not only route network traffic from one subnet to another, but it can also route data packets between the LAN and a WAN, such as the Internet. And finally, a router can also run a DHCP server that assigns IP addresses to connected clients. Here are a couple examples of routers. Most home routers include a WAN port, and often one or more additional ports that effectively serve as a built-in switch. More often than not, this is a 4-port switch, and it's in fact rare to find more than 4 LAN ports on any home router. And more often than not these days, the router also includes a wireless interface to connect Wi-Fi clients. The router on the right is an example of such a wireless router. It has antennas for Wi-Fi clients, a WAN port that you would typically connect to your modem for internet access, and 4 LAN ports that can be used for your home LAN. On the left is an example of a wired router that doesn't include a wireless interface. It only includes RJ45 ports, which are used for Ethernet cables. To connect your router, switch, and network clients, such as laptops, you need Ethernet cables. There are many standards of Ethernet cables that have evolved over the years, but the construction of these cables have some things in common. One is that they consist of 8 color-coded wires, which are always twisted in 4 pairs. In Ethernet patch cables that are used to link network devices, these 4 pairs of wires are terminated using RJ45 connectors. Ethernet cables can be constructed in different ways, and it's important to use the correct type of cable for your application. The most commonly used cables are categorized as Cat5, Cat5e, Cat6, Cat6a, Cat7, and Cat8. By using the wrong type of cable, you may not achieve the optimal network speeds that your network devices are capable of, or you might be throwing away your money by buying expensive cables that offer no speed or reliability advantages given your network devices. So let's review the differences between these cables, but before we do that, let's talk about network speeds. I mentioned earlier that inexpensive switches and routers are available that can function at gigabit speeds. The speed of a network can be described by the amount of data that can be transferred per unit of time. Commonly, we describe these speeds in megabits per second, and most home Ethernet networks that use twisted pair cables operate at 10, 100, or 1000 megabits per second, although faster speeds are also achievable. To put this into perspective, older dial-up modems operated at maximum speeds of about 56 kilobits per second, or 56,000 bits per second. Early Ethernet networks operated up to 10 million bits per second. And most home networks now operate at 100 megabits per second to 1000 megabits per second, which is a gigabit per second. Faster network speeds are also achievable, but typically not worth the expense for home networks. Aiming for 1 gigabit per second is both easily achievable and affordable in most home and small to medium-sized business networks. With a gigabit network connection, you can support over 100 simultaneous 1080p HD video streams or dozens of 4K video streams. The typical maximum length that can be used in a single run of Ethernet cable is 100 meters, and cables are therefore rated by the maximum network speed they can support over that 100-meter run. Cat5 cables support 10 or 100 megabits per second speeds at the maximum 100-meter length. Cat5e cables offer greater protection from interference and can therefore support a theoretical maximum of 1000 megabits per second, or a gigabit, at the maximum 100-meter length. Cat6 cables have no trouble supporting up to 1 gigabits per second speeds at the 100-meter length, and they can also support up to 10 gigabits per second speeds to a maximum length of about 55 meters. And by using stronger sheathing and foil wrapped around the cable conduit, or even foil wrapped around the individual twisted pairs, Cat6A, Cat7, and Cat8 cables can support even faster network speeds. But something to keep in mind is that Cat7 and 8 cables are thick, they're less flexible, and they can be quite expensive. And something else to keep in mind is that most computer-grade switches, routers, and laptops can only support up to 1 gigabit per second anyway. So the point at which there is no real gain relative to cost for network cabling is either at the Cat5e or the Cat6 point. And because the cost of Cat5e and Cat6 is nearly the same, the sweet spot for most home network applications is to use Cat6 Ethernet cabling, given its low cost and excellent performance with even long cable runs. So the last piece of network equipment needed in our network that I haven't yet discussed is the network adapter itself. Many laptops have an integrated Ethernet adapter, which can be identified by an external RJ45 port. Some laptops are slimmer than the height of an RJ45 connector, and therefore might either include an RJ45 Ethernet port with a flip-down lid, or may not include an Ethernet adapter at all. If your laptop doesn't have an Ethernet port, you can still connect it to a wired Ethernet network by adding an external network adapter, which can be connected to either your laptop's USB-A or USB-C port. Something to keep in mind is that most newer laptop Ethernet adapters support gigabit networks, but older laptops may only support much slower 100 base T networks. Although that older laptop will still work with your gigabit router and gigabit switch, any network traffic to and from that laptop will be limited to the maximum speed of the slower network adapter, in this case 100 megabits per second. Okay, before moving on any further in this module, let's take a short quiz break so that you can test your knowledge so far. On the screen, you will see 3 multiple choice questions. Get yourself a piece of paper and something to write with. Once you see the questions, pause your video, write your answers down, and then unpause the video. Okay, let's review those answers now. So question number 1, how many twisted pairs are used in a Cat5e Ethernet cable? Correct answer here is B. There are 8 wires and therefore 4 twisted pairs. Question number 2, which of the following cables support gigabit speeds up to 100-meter cable length? Correct answer is option C, Cat5e and Cat6. So Cat5 does not support that speed, therefore options A and B are off the table. Cat8 actually supports much faster than that. Question number 3, which of these devices is used to assign dynamic IP addresses to connected hosts? Correct answer is again C, a router running a DHCP server. Hopefully you got 3 out of 3 and you're ready to move on. If not, I recommend re-watching the relevant part of the video for the answer that you got wrong before continuing. So let's put all this information together with a practical example of setting up a network for live scoring of a CPC event. Our network will include laptops for the EC, ACC, DIO, referee, several judges, and an announcer. We need to decide which subnet we will use for our network. Remember from Module 1 that we can use any IP address range provided that it begins with either 10 dot or 192.168 dot. So we'll use the 192.168.6 subnet. Next, we need to add a gigabit router to our configuration to direct our network traffic and to run a DHCP server that can assign IP addresses within our subnet range. If we purchased a new router, we would first need to configure it to meet our network needs. We'll start by assigning an IP address to it. By convention, we'll give it a host ID of 1 within our subnet. Therefore, its IP address will be 192.168.6.1. We'll also need to configure the DHCP server within that router to assign IP addresses within our subnet range. Router configurations differ by manufacturer, but I'll shortly walk you through the process for a commonly used router. Our router includes a WAN port that we could connect to a modem for internet access. But because we won't be connecting our network to the internet, we won't be using that WAN port. Our router also includes a built-in 4-port switch with 4 LAN ports. If we had a small number of computers to connect to our network, we could use those 4 LAN ports. But because we have more than 4 laptops to connect to our network, we'll add an unmanaged gigabit switch to our network to provide additional ports. For our switch to function properly, it's important that we plug it into one of the router's LAN ports. It doesn't matter which of the LAN ports we use, but plugging it into the WAN port will not work, so be careful to avoid that mistake. We'll use a Cat6 cable for this application, and hopefully the choice of that particular cable type will make sense to you given that we've chosen a router and switch that have gigabit speeds. Our unmanaged switch requires no configuration and it will not be assigned an IP address. All the smart functions of our network will be handled by the router, so the switch is essentially just a port multiplier. Next, we connect all our laptops to the switch ports, again using Cat6 Ethernet cables. It doesn't matter which switch ports you use, and you could also use any of the unused LAN ports on the router if you like. We'll let the router handle IP address assignments for most of our computers by configuring the network adapters to use dynamic IP addresses. But for the EC computer, we'll need to use a static IP address. So we'll configure the network adapter on that computer to use a fixed IP address within the 192.168.6 subnet. In this case, we'll use a host ID of 50. And finally, we'll make sure the Windows firewall and any other aftermarket firewalls are turned off on the EC computer. Otherwise, the network traffic may not be able to reach that computer. So our network is nearly complete now. There are just 3 steps that I have not yet shown you how to do. The first of these is assigning a static IP address to our EC computer. The second is assigning dynamic addresses to the other laptops. And the final step is configuring our router. So let's start by setting a static IP address on the EC computer. We'll open the control panel on the EC computer by typing in the word control in the Windows search box. We'll then select Control Panel. And then from the options that open, we'll select Network and Sharing Center. Next, click Change Adapter Settings from the left-hand side. Right-click your Ethernet adapter, then click the Properties button. Select Internet Protocol version 4, then click the Properties button. Check the box that says Use the following IP address. You'll enter the desired static IP address, and the subnet mask should appear automatically, but if not, type in this value, and likely the default gateway will also appear automatically and should be pointing to the router. If that number isn't there, then just type it in manually, 192.168.6.1. Click OK, then close, and you're done. The second thing we need to do is set up a dynamic IP address on all the remaining laptops. You could potentially use static IP addresses on the other computers as well, but a static IP address isn't needed, and there is a risk of creating an IP address conflict by accidentally assigning the same static IP address to more than one computer. So the best solution here is to let the router do the work for us and assign dynamic IP addresses within the subnet range, and that way there will be no potential for IP address conflicts. So to set each of the laptops to use a dynamic IP address, we will type Control in the Windows search box and select Control Panel once again. We'll then again select Network and Sharing Center and click Change Adapter Settings from the left-hand menu. We'll then right-click our network adapter and click the Properties button. Select Internet Protocol version 4 and click the Properties button. Then enable the option that reads Obtain an IP address automatically. Click OK, then close. Now that computer has been configured to obtain an IP address automatically from the DHCP server that's running on the connected router. The final step in our network configuration is to configure our router. We need to configure the router to use the subnet 192.168.6, also ensuring that the router itself has an IP address of 192.168.6.1. And finally, we need to enable the DHCP server that's running on our router and configure it to assign addresses to our dynamic hosts that belong to the 192.168.6 subnet. Now, here's where a little bit of planning goes a long way to avoid future problems. By default, many DHCP servers will assign addresses that might conflict with IP addresses that were manually assigned on the host computers. Such IP address conflicts cause network problems. For example, if we had a host on our network that was randomly assigned a dynamic IP address of 192.168.6.50, and then we later turned on our EC computer that had that same IP address assigned as a static address, we would then have two computers on the same subnet with the same IP addresses, and our network wouldn't function properly. We might also have an IPTV video encoder on our network that has the IP address 192.168.6.200, and similarly, we would not want our DHCP server to be assigning that address to any other computers. To avoid such conflicts, we can configure our DHCP server to assign dynamic IP addresses only within a range of IP addresses, such as 192.168.6.100 to 192.168.6.199. That still gives us 100 dynamic IP addresses, which is a lot more than we need. By doing this, we can then safely assign static IP addresses with host numbers below and above that block of addresses that will be assigned by the DHCP server that will not cause any conflicts. So the next step involves configuring our router. The process for doing this differs by manufacturer. The one I'm showing you right now is from an Asus RT AC67P. It's a commonly available consumer grade and relatively low cost router. The picture on the right is the back view. You can see it has a blue port. That's a WAN port. We will not be using that port in this configuration because we do not require internet access. And on the right-hand side is a 4-port switch or 4 LAN ports, and we will be connecting our computer to one of those. So according to my router's user manual, all I have to do to connect to the interface is open a web browser and go to the IP address or to the domain address http://router.asus.com. And that opened this interface here. It's maybe worth mentioning that prior to plugging my laptop into the LAN port on the router, I set my network adapter to use a dynamic IP address so that the router would assign an IP address. That's to make sure I'm on the same subnet as the router, because if I wasn't, I wouldn't be able to talk to the router. So one of the first things I notice on this dashboard is that the LAN IP address of the router is wrong for my purposes. So this one ends in 1.1, and I am hoping to set up a subnet that ends in 6.1. So first thing I need to do is change that by clicking the LAN button on the left. Then the next thing to do is enter the correct IP address in this box here, 192.168.6.1. And the subnet mask, that is the default, actually looks fine. Then click the Apply button. Okay, looking at the dashboard now, we have the desired IP address for the router, so that's fantastic. Next thing we need to do is configure the DHCP server. We click the LAN button again, go to the second tab, and so here is the problem that I mentioned earlier. So by default, this DHCP server will assign any IP address between 2 and 254, or any host name between 2 and 254, and that could cause problems. So I'm going to reconfigure this so that the lowest IP address will begin with the hostname 100 and the highest will begin with what will be the hostname 199. That way I will have 99 addresses below that 100 hostname that I can use for manual IP address assignments without worrying about creating any kind of IP address conflicts. After those settings, click the Apply button, and our router is configured. So the last thing to do now is to check to make sure it's working properly. So I'm going to open a command prompt. I actually have a shortcut here in my menu bar, but another way of opening a command prompt is to type the word command in the search box and press enter. And then I'm going to type in the command ipconfig and press the enter key. And that will show the IP address and other network information for all of your network adapters. So in this case, I'm only interested in what's listed under the Ethernet adapter. And here I can see that I have an IP address that is in the correct subdomain. That is the 192.168.6. And it has correctly assigned an IP address within the target range with a host number falling between 100 and 199, exactly as I wanted it to do. So this is working as expected. Our network is now configured properly. If these were new laptops, all that would be left to do is to run the complete installers of the latest version of CSS on the EC and ACC computers. We would also need to install the CSS announcer module on the announcer computer and the latest version of LTS on the DIO, referee, and judge laptops. Then we would need to set the competition database IP address on all these computers so that they point to the SQL database server running on the EC laptop. On the EC computer, we would configure CSS to point to the localhost database by using the setting localhost /SQL Express 2014. On all other computers, we would configure CSS or LTS to point to the database hosted on the EC computer using the setting 192.168.6.50 /SQL Express 2014. The second scenario involves setting up a local area network for a manual entry competition. For example, we might want to have 2 people enter results for different skaters simultaneously using 2 laptops that both point to the same competition database. You might also want to be able to print to a network printer from either of these laptops. This is actually a simpler setup than was needed for a full CPC setup because we don't require a switch. We still need a router, but instead of a switch, we can just use the LAN ports that are built into our router. We'll again use Cat6 Ethernet cables to connect the router to our laptops, and we'll also run a cable to our network printer. If you don't know if your printer is easily networkable, just look for an RJ45 port, which is typically located next to the printer's USB port. We'll again need to decide which subnet we'll use for our network. In this case, let's use 192.168.6 again because our router is already configured for that subnet. but you can make this whatever you like. We'll then need to choose IP addresses for our laptops and printer. The laptop hosting the competition database, which I'll call the master, will need a static IP address so that it remains stable over time. We'll use 192.168.6.50 for that. The printer should also be given a static IP address so that its location on the network also remains stable. Otherwise, we would have to repeatedly reconfigure our printer drivers. By using a static IP address on the printer, we can set up our printer just once, and it'll keep working. We'll use 192.168.6.75 for the printer. The second laptop, which I'll call the slave, doesn't require a static IP address because it's not hosting the database, and it therefore doesn't matter if its IP address changes over time. So we'll set that one to obtain an IP address automatically. That is, we'll set it to have a dynamic IP address. Most network printers have a small LCD screen that can be used for setting options. Under the network setup options of your printer, you can choose whether you want to enable the Ethernet adapter and how you want the IP address to be assigned. You'll usually find an option to have it assigned by DHCP or to use a static IP address. After choosing the correct option for your printer, enter the IP address 192.168.6.75. a subnet mask of 255.255.255.0, and a gateway or router of 192.168.6.1. You might have to restart your printer for the new settings to take effect, and then your laptops should be able to find your printer on the network. Then, all that's left to do is configure the competition database on both computers. On the master computer, we would configure CSS to point to the local host database by using the setting localhost /SQL Express 2014. On the slave computer, we would configure CSS to point to the database hosted on the master computer using its IP address. That is, using the setting 192.168.6.50 /SQL Express 2014. Don't forget to turn off the Windows firewall on the master computer so that the network ports needed to route traffic to the database don't get blocked. And that's about it. That completes this small network setup. You'll now be able to have 2 or more data specialists manually enter results for different skaters simultaneously. This can also come in handy in a situation where you'd like to be able to print reports, or anything else for that matter, from more than one computer, instead of having to rely on only one computer that's attached to the printer with a USB cable. So that takes us to the final network application that I plan on covering in this second module of this video series. What I plan on covering now is the networking requirements of a video replay system. Now, there are different video replay systems and network configurations that are used across the country. And in fact, the system that we use for the Skate Ontario competition scoring systems somewhat differs from the system that's used by Skate Canada at Challenge and Canadians. So if any data specialists from outside of Skate Ontario happen to be watching this video, please keep in mind that the information that I'm presenting in this next segment may or may not apply to the system that's used by other sections. So let me start by quickly reviewing the equipment that's used by Skate Ontario for video replay. A video camera with HDMI output provides a video feed to an IPTV video streaming box made by JTech. Typically, the data specialists just refer to this as a JTech box. It converts the HDMI video signal received from the video camera to a 1080p resolution video that's encoded using the H.264 codec, which is just the format of the video signal that's being used. And in this case, this H.264 is the most commonly used video encoding format that's used in the world today. Although that's actually gradually changing to a more advanced but not quite as compatible codec called the H.265. So that H.264 video stream is received by our VRO computer and then translated or decoded from the H.264 format back into a video signal that can be displayed on the screen, and also manipulated using software, which in this case is a piece of software provided by the ISU called Cutter, or ISU Cutter. Under the direction of the TC, the video replay operator, or VRO, replays elements so that the technical panel can deliberate on the element calls. And that's accomplished by having the TC and the TS and the ATS crowd around an external monitor that's connected via an HDMI cable and displays the same video that's being controlled on the VRO laptop. So you might be wondering, if the video camera is providing an HDMI feed and the VRO computer is ultimately displaying an HDMI signal too, then why not just connect the video camera to the VRO computer by a long HDMI cable and dispense of the need for a video encoding box and Ethernet altogether? Well, the reasons for this are twofold. On the one hand, doing this would require 2 HDMI ports on the VRO laptop, and the work of converting the signal from HDMI to something that can be used by Cutter would fall on the laptop, and it's best to not overload the laptop's video processing capabilities. But an even more important reason is that HDMI cables are not capable of transmitting high-definition video signals long distances. For 1080p video, the maximum length of an HDMI cable is 15 meters, and that's under ideal conditions. So in practice, the length is even more limited. We can instead place a video encoding device, or JTAG box, close to the video camera, and then we can run a long Ethernet cable to carry that encoded video wherever we like without worrying about the distance, because a Cat6 Ethernet cable can function optimally at gigabit speeds with cable runs as long as 100 meters. Let's now look at this mini network used to connect the JTAG box to the VRO laptop. There are actually a couple of different ways that these devices can be connected. One way is to simply connect them by running a single Cat6 Ethernet cable from the JTAG device to the VRO laptop. In this type of configuration, no router or switch is required, and this bare bones network runs completely independent of the competition scoring network. In this type of configuration, it's critical that a static IP address is assigned to the VRO computer because the network lacks a router. So there's no DHCP server to assign a dynamic IP address. The Skate Ontario JTAG devices have all been configured to use a static IP address of 192.168.6.200. Therefore, in this configuration, we would need to assign a static IP address to the VRO laptop that also belongs to the 192.168.6 subnet. Otherwise, the two devices would not be able to connect to each other. So, for example, we could use 192.168.6.60. I will, however, provide a word of caution that connecting directly the JTAG box to the VRO laptop in this way might require the use of a crossover cable. An Ethernet crossover cable is a type of Ethernet cable that allows two devices, such as two computers, to be directly connected to each other without the need for a network router or switch. In a typical Ethernet network, devices are connected to a router or switch using straight-through cables, which have the same wiring configuration on both ends. However, when two devices are directly connected to each other, they both sometimes require a different wiring configuration. This is where a crossover cable comes in. A crossover cable has one end wired for the transmit signal and the other end wired for the receive signal. So this allows the transmit signal from one device to be connected directly to the receive signal of the other device and vice versa, enabling the two devices to communicate with each other. Having said that, not all devices require a crossover cable for direct connection because many modern Ethernet devices can automatically detect the wiring configuration and adjust accordingly. However, if you're connecting to older devices or a device that doesn't have automatic crossover detection, then a crossover cable becomes necessary for this kind of direct communication. As far as I've been able to tell, the JTAG box that's used by Skate Canada, Skate Ontario, and likely some other sections, does have automatic crossover detection. So as long as your laptop's network adapter also has this capability, then you should be fine to use a direct connection using a straight-through cable. That is, no crossover cable is needed. A second option for networking your JTEX video streaming device to your VRO laptop is to connect both to a router. By doing that, you definitely will not need a crossover cable, and it also doesn't matter whether you assign a static IP address or a dynamic IP address on the VRO computer. So this is a more, I guess you could say, robust method of networking your video replay system. One drawback, though, is that you'll need a router, but because you'll likely already have a router and switch connecting your other laptops, you can simply plug into that same network. If you're concerned about the video signal interfering with your CSS scoring equipment, there's really no need to be concerned because the 1080p video stream that you're going to be putting onto the network only uses less than 1% of the available network bandwidth. Now, if you'll be connecting your VRO and JTEX box to your router, you'll need to ensure that the static IP address on the JTEX box matches the subnet that's being managed by your router. For example, the factory preset IP address on the JTEX box, so when you first buy it, or if you were to do a factory reset, is 192.168.1.168. If you don't change that factory default, and then you plug it into a router that's configured for a subnet of 192.168.6, none of the computers on your subnet, including the VRO, will be able to communicate with the JTEX box. In the case of the JTEX boxes that are used by Skate Ontario, they're all configured to use the static IP address of 192.168.6.200. And the routers that are used for the competition scoring systems are all configured to use the 192.168.6 subnet. Therefore, these devices can be connected together without having to modify any settings. If your section is using the factory default IP address of 192.168.1.168 for your JTEX box, then you'll need to ensure that the router being used to network it with your VRO laptop is configured to the 192.168.1 subnet. Okay, let me switch this back to the typical Skate Ontario system that uses the .6 subnet. I mentioned earlier that when the JTEX box and the VRO laptop are connected indirectly via a router, or in fact a switch connected to that router, then you have the option of using a dynamic or a static IP address on the VRO laptop. I actually recommend, in fact strongly recommend, that you always use a static IP address on the VRO laptop. I say this because if you were to assign a dynamic IP address on the VRO and connect the JTEX box on the VRO through a router, it will work fine. But then later on, if somebody plugs the JTEX box directly into the VRO laptop, then the video replay system will not function because the VRO laptop would be looking for a non-existent DHCP server to assign its IP address. By always having a static IP address on the VRO laptop, it'll be able to communicate with the JTEX box whether it's connected directly to the box or indirectly by going through the competition scoring system router or switch. Okay, we are nearing the very end of this second module. Let's just pause again for a quick quiz to test your understanding of the information that we've covered so far. So here are 3 more multiple choice questions. You'll want to pause the video now, write down your answers to these questions, and when you're ready to see the answers, unpause the video. Okay, let's review the answers. Question number 1. To determine the current IP address of a laptop running Windows 10, open a command prompt and type, which command? Correct answer is A, ipconfig. This is maybe a bit of a sneaky question. I didn't spend too much time on that. the entire Module 3 is dedicated to troubleshooting networking issues, and we'll certainly be talking a lot more about these sorts of commands at that time. So what ipconfig does is it shows you the IPv6, the IPv4 address, the subnet mask, and the default gateway for all of your network adapters, so including your Ethernet adapter and also your wireless adapter. Okay, question number 2 presented you with an IP address for the EC computer and also for the router, and then it asked you to identify the correct CSS database location that should be used on the other computers. So the correct answer here was option E. So we always want the other computers to be pointing to the EC computer. So the EC computer's IP address ends in 32.100. Therefore, our correct answer will be there. And you'll notice that answers D and E are similar. One of them has a /, which is incorrect. One of them has a /, which is correct. And CSS is really particular about this. If you use the wrong slash, it will not function. So always make sure to use the /. Okay, question number 3 presents you with a router that has been configured to a particular subnet, 192.168.2, and then it asks you to set up a valid static IP address for your master laptop. So the correct answer here is D. All but one of these IP addresses actually use an incorrect subnet. So option D is the only one that uses a subnet of 2. Hopefully you got 3 out of 3 questions correct, but if not, be sure to go back and review the relevant segment of the video that covered that information. This takes us to the end of Module 2. Our next module will cover troubleshooting networking issues.